Hello, Quantitative Methods class. What we're going to discuss in this lecture is just go over some of the basic principles that we need to understand before we can get to inferential statistics. And remember, inferential statistics are all about inferring qualities about the population. And this is ultimately what we're interested in for the majority of psychology studies. We might conduct some experiment when we have an experimental group and a control condition, and we might find some mean differences. But does that mean that those mean differences truly exist in the population when we look at everybody, that those differences are not just due to random fluctuations, just due to chance, just due to the fact that we randomly assigned this group of people as opposed to another group of people? So ultimately, we care about, are there differences in population means? Or differences in means in the population. So we need to make some inferences. So to do this, we're going to need inferential statistics. So in this lecture, we're going to talk about two things. We are going to discuss sampling distributions. What are sampling distributions, why they are important. And then we're going to talk about the predominant, most popular way in which psychologists go about doing inferential statistics, and that's via Null-Hypothesis significance testing, which is a mouthful. Sometimes we abbreviate it as NHST. Now, Null-Hypothesis significance testing is the way that we've done things for about a century. There are many advantages to this way of conducting inferential statistics, but there's a lot of limitations to it as well. But first, let's talk about sampling distributions. What's a sampling distribution? So, a sampling distribution is a distribution like what we looked at in our last lecture, but it's a sampling distribution. I mean, it's a distribution of a particular statistic. So it could be a standard deviation, a distribution of standard deviations. It could be a distribution of means. Most commonly, it is means. Okay, we're having a distribution of means. And what we do for a sampling distribution is we go out into our population and we randomly select a certain number of subjects. We're going to use the term N to refer to the number of observations or the number of subjects that we have. So we go into the population and grab N people. Now we take them back and we are going to run our experiment, measure whatever it is that we're interested in, and calculate what that sample mean is. And we're going to record what it is. And then we're going to throw them back into the population like we would fish if we're not going to eat them. And then we're going to do the process again. We're going to go back into the population and randomly select N number of people, the same number as before, take them back, record what their mean is on whatever dependent measure of interest, and then toss them back. And we're going to do this infinite amount of times to see what these means are going to look like. And then we're going to form a distribution of these means. Some means are going to be more frequent than others. Sometimes when we go out and randomly sample people, we might grab these same exact people, especially if the population is fairly small. So sometimes we are going to have the same subjects in multiple samples. Here is an example of something that we might do for our sampling distribution. Imagine, if you will, that this entire rectangle is everybody in the population. So if we're doing a sampling distribution, we might randomly sample people within this green circle, calculate their mean, write it down in our notebook, and do the same thing for infinite amount of times. Here we see 5 separate sample means. And notice that there is some overlap between some of these samples. Now we eventually do this and we're going to write down what this sampling distribution looks like and some qualities of the sampling distribution. If we were in class, my graduate professor taught me a cool dance that demonstrates what we do for sampling distribution. But unfortunately, I can't do it for you guys or have you guys participate in that. So what does a sampling distribution look like? Here's some examples of sampling distributions. Notice that sampling distributions are normal or are fairly normal. for the most part. And notice that the variance of the sampling distribution depends on the number of subjects that we have in our sample. Notice that the more subjects that we have, the less variance we have, and the more those means are clustered around the mean of the means, if you will. If we have a small number of subjects, we're going to have more variability in our sampling distribution. Our sampling distribution is going to be wider. And this makes sense. The more accurate, the more subjects we have, the more accurate our measurement is going to be. And the closer our mean is going to be to what the true mean is in the population. If we only have one subject or two subjects, we might select the two most outliers, the outliers here. However, if we have a larger N, we have more subjects, we're going to get closer to what the true mean is. We're very unlikely to have a sample mean that's very aberrant, that's very abnormal. So there are three qualities of sampling distributions that I want us to pay attention to. The mean of the sampling distribution, that's what mu is. Remember, this is our Greek character mu, which is our population mean. Mu sub x bar, this is our sampling distribution population mean, is equal to whatever the true population mean is. So whatever the true population mean is of our particular score, the mean of our sampling distribution is going to be that exact same thing. So that's quality number one. Quality number two of our sampling distribution, the variance of the variance of our sampling distribution is known to us. The standard deviation of our sampling distribution goes by a special name. It goes by the name of standard error, or the standard error of the mean. Sometimes it is abbreviated SE or SEM. So the standard deviation of our sampling distribution is called the standard error. And the standard error is equal to, in the numerator, what the true population standard deviation is in the population. What is the true standard deviation? Divided by the square root of n. And remember, n is the number of subjects that we keep sampling. Might be 5 of them, might be 10 of them, might be 100 of them, whatever n is in this particular situation. So notice what happens. The less natural variability there is, the smaller the standard error is going to be, the more compact our sampling distributions are going to be. And also, the more subjects that we have. If we go from 10 to 100 subjects, that's going to lead these sampling distributions to get more compact, to get less variable. So quality number two of our sampling distribution is we know what the standard deviation of it is. It's called the standard error and is equal to the population standard deviation divided by the square root of n. Now, property number three has a special name. It's known as the central limit theorem. And the central limit theorem has two parts to it. The central limit theorem describes the shape of the sampling distribution. What is the shape that the sampling distribution is going to take up? And the central limit theorem states, part number one, that if we have 30 or more subjects in our sampling distribution, if we have 30 or more subjects, our sampling distribution is always going to be normally distributed. It doesn't matter what the population distribution is. So if the population distribution is bimodal, an ugly distribution like this, if it's skewed, and remember, since we have the tail over here, this is positive skew. If it is platykurtic, it doesn't matter what the population distribution looks like. The sampling distribution will be normally distributed. So here's our sampling distribution, our distribution of all of these sample means, and it's normally distributed as long as we have 30 or more subjects. That's part one of the central limit theorem. Part two pertains to when we have less than 30 subjects. If we have less than 30 subjects and we're doing a sampling distribution, If the population distribution is normally distributed, then the sampling distribution is going to be normally distributed. So if the population distribution is normally distributed, our sampling distribution is going to be normally distributed. But if our population distribution is funky looking, it's not normal, it's bimodal, it's skewed, it has a problem with kurtosis, then and we have fewer than 30 subjects, we don't know what the shape of the sampling distribution is going to be. We just don't know. It's going to be more normal than the population distribution, but it might not approximate what a normal distribution is. So, problem time. Let's do the following question. So a researcher selects a random group of 36 students at UNG to get their opinion on a hot button issue, and students rate their opinion on a 110-point Likert scale. I did that. You would never do a 110-point Likert scale, but I did it so that the graph would make sense here. We have a mean population of UNG of 60 on this issue, and the population standard deviation is 24. The data are displayed on the graph below. What is the shape of the sampling distribution? What is the mean of the sampling distribution? And what is the standard error of the sampling distribution? Now, if we already know what the population mean is and the population standard deviation, it doesn't make sense to really look at a sampling distribution, but we're going to do this problem because we're going to deal with sampling distributions when we get into our inferential statistics. So let's ask some questions about what the sampling distribution would look like if we randomly grabbed 36 people from this population distribution. Well, first of all, let's talk about the shape. First thing that we want to note is how many subjects we have. If it's 30 or more, the sampling distribution is going to be normally distributed. If it's less than 30, we have to look at the population distribution. And if it is normally distributed, then our sampling distribution is going to be normally distributed. If it is funky looking, then we don't know the shape of the sampling distribution. We have more than 30 subjects, so we know that the sampling distribution is going to be normally distributed. It doesn't matter the fact that this looks like a bimodal distribution. However, if I were to say that the number of subjects were 25, we would have to respond, we don't know what the shape of this distribution is going to be, sampling distribution. What's going to be the mean of the sampling distribution? The mean of the sampling distribution is always equal to what the true population mean is, so it's going to be 60. How about the standard error, or the standard deviation of the sampling distribution? It's going to be equal to whatever the standard deviation of the population is divided by the square root of n. N is 36, the square root of that is 6, so 24 divided by 6 should give us 4. Let's see what I got here. Boom. Yeah, I can do math in my head. So for your second homework, we're going to have some problems on using the normal curve, standardized scores, and looking at sampling distribution problems. So let me know if you have any problems with those. So let's move in and talk about how we end up conceptualizing inferential statistics, and this is via null hypothesis significance testing. So first, let's talk about some of the problems that we might encounter when we're looking at inferential statistics. So again, inferential statistics, statistics in which we're trying to infer something about populations. So trying to evaluate population parameters from sample statistics. Okay, so here's an example. So are UNG students better at psychology than UGA students? So let's say that we take a standardized test of psychology ability. Maybe it's something along the lines of the Major Fields test that if you're a psychology major, you'll take your senior year. And let's try to see what we find. So we do this, and we are going to randomly select 10 UNG students and 10 UGA students and give them a psychology test. And here's what we find. We find that the UNG mean is 85 and the UGA mean is 82. UNG, UGA. Okay. So hopefully that I won't confuse those two. It's a bit of a mouthful. Are you convinced that UNG students truly have higher psychology scores than UGA students? We might say, no, you didn't sample enough people. It's only 10. Maybe you selected the smartest people at UNG and you selected the dum-dums at UGA. Maybe, maybe not. Maybe if we were to do this again, we would find that UGA outscores UNG. So there's all of these random fluctuations in these scores. How do we truly know that there is a population difference, that these two population means of psychology test scores are different for these two groups of students from these two colleges? So that's where inferential statistics comes into play. We can look at the magnitude of the difference, and we can look at the number of subjects that we have looked at. The more subjects, the more precise these sample means are going to be, and determine if the difference is so large that it's unlikely to have been found just due to chance. But here's another point here. No matter what mean difference we have, if UNG we found was 20 points higher than UGA, we could still have found that difference just due to chance. But we've got to make a decision. There has to be some cutoff where we say, boom, this difference is so great that it is unlikely to have been done by chance. Unlikely to have been found by chance. So we say that this difference warrants us to come to the conclusion that there is truly a difference in the population means of psychology test scores between these two groups. Okay, so that's what we're going to do here. We need to find that cutoff. What is that cutoff going to be? How about some other questions? So maybe we have the following question. The population score, the population average on a measure of anxiety, maybe it's Beck's anxiety scale, is 5. Is it the case that people that own a dog, the anxiety scores are less than or maybe different from the national average of 5? Maybe dogs lead to a reduction in anxiety. Here is my dog, Tara. She is a cute girl. She is a wonderful dog. So maybe we want to see if the numbers of people that own a dog, their anxiety scores are less than the national average. This is another example where we would use inferential statistics. If we are doing a drug study, we want to tell whether or not the symptoms of depression are different between individuals that took the experimental drug and the condition in which the subjects took a placebo. Maybe we want to examine 2 different ways in which students study and try to see which ways of those are the best way that in the population people remember more with this study technique compared to this other study technique. All of the questions in psychology that we're trying to address typically deal with inferential statistics. So it's very important that we understand what's going on here. Now, a little bit of a history lesson. In the early 1900s, there was a debate about whether or not the appropriate way of doing inferential statistics. And there were 2 camps. There was camp number 1 with Sir Ronald Fisher, and there was camp number 2 with Egon Pearson. Pearson is a name that you should be familiar with, the Pearson correlation coefficient, which we will be talking about next Monday. But Pearson's probably something that you remember. So there were 2 different camps about the appropriate way to do inferential statistics. Now, Sir Ronald Fisher decided that the way that we should go about deciding if there's truly a population mean difference between 2 different conditions, between 2 different samples, is by calculating what's known as a p-value. Now, a p-value is the probability that we would have obtained this difference, or a difference more extreme than the one that we found, just due to chance, just due to random fluctuations in score, just due to random selection error. Maybe we selected the smart individuals at UNG and the dum-dums at UGA. What's the probability that that would have happened? The probability that if there's no effect, that we would have found a difference as large as this or greater than this. So we calculate this p-value. We do some math, calculate the p-value, and then report what that p-value is so that people reading our papers can decide whether or not they want to say, yep, this seems to be a logical difference in these population means. It's very unlikely, maybe there's a 1% chance that it occurs due to chance, so I'm going to say that, yeah, for all intents and purposes, these population means are probably different from one another. So Ronald Fisher decides that we should calculate these p-values. And we are going to use p-values ourselves. Psychologists are obsessed with p-values. The cutoff that we are typically going to use is that of 0.05. This is a cutoff that if we find a p-value that is less than 0.05, and a p-value of 0.05 means that the magnitude of differences that we found could have occurred 5% of the time just due to random chance. If the p-value is less than that, what we are going to do is we're going to argue that there is truly a population mean difference between these conditions, between these two sample means. Okay, that's Sir Ronald Fisher. The other way of doing inferential statistics was null hypothesis significance testing. And this was put forward, oh, I don't have them here, I'll show you in the next slide, Jersey, Neyman, and Egon Pearson. So for null hypothesis significance testing, what we do is we create two hypotheses. There is a null hypothesis, which states that there are no differences in our population means, and there is an alternative hypothesis. The alternative hypothesis is the hypothesis that we're interested in. It is that there is a difference, that this mean is greater than this other mean in the population. The null hypothesis is the hypothesis that we're not interested in most of the time, that there are no differences. So the way that we're going to provide evidence for the alternative hypothesis, again, the hypothesis that we're interested in, is to prove the null doesn't account for the data well. And if we can show that the null hypothesis doesn't account for the data well, we reject it. And this is going to provide evidence for our alternative hypothesis. So let's go into this in a little bit more detail. The null hypothesis, this is the default position in which there's no effect in our study. There is no population mean differences. Our manipulation had absolutely no effect on the dependent measure. For example, this might be there are no differences in the population means between our two groups or between our two conditions. Any observed differences in our sample means are due to sampling error. They're due just to chance. So maybe, excuse me, some examples would be there's no difference in the anxiety scores between people who own a dog and the general population. There are no difference in the population mean psychology test scores between UNG and UGA students. And we can contrast the null hypothesis with the alternative. This is the exact opposite of the null hypothesis, contrary to the null hypothesis. It's usually taken to mean that there are some differences in the population means. There is some effect of our independent variable. So there is a difference in anxiety scores between people who own a dog and the general population. There is a difference in the population mean psychology test scores between UNG and UGA. So there is a difference here. So the logic that we're going to do is we're going to test how well the null hypothesis fits the data that we have. If the null hypothesis fits the data well, we retain the null hypothesis. We do not provide evidence for the alternative. If the null hypothesis does not account for the data well, then we reject the null hypothesis. And this is going to provide evidence for the alternative hypothesis. Okay, So we make one of two decisions. We are either going to reject the null hypothesis if there's enough evidence to support that the null hypothesis is not tenable. It's unlikely to have accounted for our results. The probability that we would have found this result if the null hypothesis were true is very unlikely. So we either reject the null hypothesis, or we retain or fail to reject the null hypothesis. We never accept the null hypothesis. There could always be a difference that's so very small that our statistical test is unable to pick up this difference. So we never accept the null hypothesis. We always either fail to reject or retain it. And you can use those two terms interchangeably. So how do we decide whether or not to reject or retain the null hypothesis? What we do nowadays with null hypothesis significance testing is we take the approach of Neyman and Pearson and the approach of Fisher, and we kind of combine them together. We're going to calculate a p-value for every single study. And if the p-value is less than 0.05, which is an arbitrary value that psychologists have just managed to decide on, a 5% chance that if the null hypothesis is true, we will reject the null hypothesis. If our p-value is less than 0.05, we reject the null hypothesis. We say that there's truly some population mean differences. Otherwise, if the p-value is greater than 0.05, we retain the null hypothesis. We do not accept the null hypothesis. So for instance, if we find that the p-value is less than 0.05, we say that there is a difference between our two groups, and that the difference between our two groups is statistically significant. We might also say that the sample means are significantly different from each other. What we do not say is we do not say that our results are ever insignificant. They are not statistically significant, or they are statistically significant. They're never insignificant. Insignificant implies that the results are not useful, and our results could still be very useful even if they're not statistically significant. Maybe it's the case that the null hypothesis actually is true. And if we find that we have to retain the null hypothesis, it doesn't necessarily mean that our results are useless, so we never say that they are insignificant. So no matter where we put this cutoff of where we reject the null hypothesis or retain the null hypothesis, we always have a chance that we're going to make an error. If the p-value is 0.05, this means that there's a 5% chance that we would have found these results just due to random fluctuations. So there's two kinds of errors that we can make. One is a type 1 error. Our type 1 error, we might refer to this as a false positive. This is where we reject the null hypothesis when the null hypothesis is actually true. And the way that psychology experiments are set up most of the time, if the null hypothesis is true, we have a 5% chance of committing a type 1 error. And then we have a type 2 error. The type 2 error is where we have a population difference that truly in the population, these population means are different from one another. But we retain the null hypothesis. So this we might refer to as a miss. There's truly a difference, but we say that there is not one, or we retain the null hypothesis in this particular situation. The probability of making a type 1 error goes by a special name and has a special symbol. It's called alpha. So our type 1 error rate is equal to alpha, and we can see this alpha on our screen here. We set alpha at the beginning of our study, and that alpha error rate is typically 0.05. That's what we have decided as psychologists. It's an arbitrary value. It's just what somebody decided one day, so we're going to stick with it. The probability of making a type 2 error is known as beta, and we can see the wonderful beta sign here. Typically, we do not know what our type 2 error rate is. We set the type 1 error rate. We don't set the type 2 error rate because we never know what is the true magnitude of the difference between our population means. So we never really know what our type 2 error rate would be. We can guess at what it is, but we never quite truly know. So this leads us to this graph here. There are 4 potential outcomes that we can have when we're doing null hypothesis significance testing. If in reality the null hypothesis is true, that there are no mean differences in the population between UGA and UNG, and we decide that we are going to retain the null hypothesis, we make a correct decision. It's not as interesting, there's no differences, but we make a correct decision. However, if we reject the null hypothesis, again, this might happen 5% of the time, just due to random chance, we commit a type 1 error. However, if reality is that the null hypothesis is false, there's truly some mean differences, and we decide to reject the null hypothesis, again, we make a correct decision. We get a publication out of it, good for us, and clap. But if there's truly a population mean difference, if the null hypothesis is false, and we decide to retain the null hypothesis, we're committing a type 2 error. So that's problematic. There are 2 kinds of inferential statistics tests that we can do, just comparison between 2 means. One is where we do not have a hypothesis. We have no hypothesis. In this case, we do not know the direction of the effect. And so what this kind of test is going to be called, it's going to be called a two-tailed test. I'll talk about why it's two-tailed here in a second. A one-tailed test is where we have a prediction in the direction of the effect, that the population mean for UNG is higher than that of UGA. So with a one-tailed test, we have a prediction. We know the direction of the population means. A two-tailed test, we do not know the direction of the population means. So for a one-tailed test, maybe we are predicting that the mean of the first group will be bigger than the mean of the second group. So we have some kind of prediction. Here's 2 graphs of our two-tailed and one-tailed test. Now what we're doing here is we're drawing a sampling distribution. A sampling distribution if the null hypothesis were true. And if we find a sample mean that's in this particular region of this sampling distribution, then we're going to reject the null hypothesis. So we set up a rejection region that if we find any value that is over or within that rejection region, it's past this particular cutoff value, we decide that we're going to reject the null hypothesis and say that there's truly a population mean difference. For a one-tailed test, since we know where the population mean difference is going to be, we set our rejection region to only one side of our sampling distribution. So one-tailed test, the rejection region is in only one tail of the sampling distribution. For a two-tailed test, however, we don't know if the population mean for UGA is going to be smaller or greater than that of UNG. So in this case, we need to have 2 rejection regions. One in which the rejection region is going to be to the right of the distribution, and the other one's going to be to the left part of the distribution. And since we want to make sure that we only have a 5% of the time, if the null hypothesis is true, we're going to make a type 1 error. We're going to divide our type 1 error rate, alpha, so that 0.025 or 2.5% of the time, we're going to include that on the left side of the distribution, and the other 2.5% of the time we're going to put on the right side of the distribution, such that these add up to 5% of the time of us potentially making a type 1 error. We'll get more into this, not next week, because next week we've got the exam and the differential psychology lecture. But our last week of this class, we'll go more into some details about this. Last thing, let's talk about how we can decrease the probability of making a type 1 error. Well, we can decrease the the probability of us making a type 1 error by lowering that alpha level. Instead of it being 0.05, let's make it 0.0001. But if we do this, this is going to have a lasting impact. We're less likely to reject the null hypothesis if this were the case. So most of the time we leave the type 1 error rate be at 0.05. We're not going to decrease it any, because otherwise we would not be able to detect any effect whatsoever. It'd be very hard to find it. How do we decrease the probability of a type 2 error, of there being a true population mean difference between our two conditions, but we are still retaining the null hypothesis? Well, there's a few things that we can do. One is we can increase the type 1 error rate. Okay, instead of it being 0.05, we can make it 0.1. But what this is going to do is we're going to be less likely to commit a type 2 error, but more likely to commit a type 1 error. So there's a push and pull there. So we don't like that. We're going to set it at 0.05. We don't have any of these 0.1 alphas or anything like that. So we can't do that. That's not going to help us out. One thing that can help us out, if we have a hypothesis and we switch from a two-tailed test to a one-tailed test, this is going to increase our likelihood of not committing a type 2 error. It's going to increase the likelihood that we're able to reject our null hypothesis if there's truly some population mean differences. So switching from a two-tailed to one-tailed test is a good idea if we have a hypothesis. Another thing that we can do that's very simple is increase the number of subjects that we have. If we increase the number of subjects that are in our experiment, the less likely we are to commit a type 2 error. Again, remember what happens to the variability of that sampling distribution. We're drawing a sampling distribution based off of how many subjects we're sampling, if the null hypothesis were true. And that sampling distribution is going to get more and more compact the more subjects that we have. The standard error of the mean is equal to the population standard deviation divided by the square root of n. N is the number of subjects that we have. The bigger that is, the smaller our standard error is going to be, the more compact our sampling distribution is going to be, the more likely we are to reject the null hypothesis. And we like to find effects. We find an effect, that's a publication, find something cool. The last thing that we can do is we can strengthen our manipulation. So perhaps we are looking at the influence of a specific study technique. And maybe instead of doing that study technique for 1 day, we do it for 5 days. That's more likely to have an effect. Maybe instead of giving 20 milligrams of the drug, we give 50 milligrams of the drug. Again, this is likely to increase the probability of there being an effect, because the population mean difference is going to be magnified because we've strengthened our manipulation. So those are just some points that are very important for inferential statistics. So make sure that you study those, and we'll get more into these the last week of classes. Okay. I hope you guys are doing well. Keep things up. Make sure that you email me if anything comes up. I am more than likely to help you out, but I just need to know. So have a wonderful day, and I will talk with you guys later. Bye-bye.